Now next topic, equivalence class. Now to understand this topic, definition, whatever is written in this paragraph, terminology related to this word equivalence class, to understand this everything, I will take this example. So by this example you will be able to understand very easily. Otherwise, if I will explain directly, you will not able to understand what is the meaning of these statements. So first of all, I am taking this question, then I am coming on this definition. So here first part of question is, show that the relation are in the set Z of integers given by R is equal to set of ordered pairs AB such that 2 divides A minus B. Show that this is an equivalence relation. This is first part of this question, and already we discussed what means equivalence relation. So to show that this relation is equivalence, we shall prove that it is reflexive, it is symmetric, and it is transitive. So relation is, it is defined, this is a relation in set Z. It is a relation in Z, so A and B are any integers. A and B we will be taking from Z. So here condition is that this is the order pair such that 2 divides A minus B. That means, say if I take suppose 5, 1, A is 5, B is 1, this is A, this is B. Now check A minus B. So A minus B is 4, and say 2 divides 4. So condition is satisfied, 2 divides 4. So therefore EB 5, 1, it is in this relation R. If I take minus 7, 1, minus 7 is integer, 1 is integer. Now what is A minus B? So A minus B is minus 8, and 2 divides A minus B, 2 divides minus 8, that is true. So this is belonging to R. If we take suppose minus 7, minus 12, this is A, this is B. Now A minus B is minus 7 minus 12, it is 5. But 2 does not divide A minus B. So this element does not belong to R. So R is the set of ordered pairs such that difference of A and B, that is A minus B, first value minus second value, this value is divisible by 2. In short, if this is even, then ordered pair AB belongs to R. Otherwise, if difference A minus B is odd, so it is not divisible by 2, so this element does not belong to R. So first of all, you should know that what is the meaning of condition, which type of elements are belonging to R. So accordingly, we are going to give here statements. Now first property is reflexive. For reflexivity, we take any element from Z. For any element A belonging to Z, we want to show that AA belonging to R. If for any A belonging to Z, AA belongs to R, then R is reflexive. Now AA belongs to R is true if 2 divides A minus A, and it's true. For A belonging to Z, it is true that 2 divides A minus A, because A minus A is 0. 2 divides 0, that is always true. 0 is divisible by every number. So 2 divides 0, that is true. Therefore, AA belongs to R. Therefore, R is reflexive. Now, second property. Is it symmetric? So, to check symmetricity, we take any element from R. Let AB be any element in R, and we want to show that its inverse BA. If BA belongs to R, then it is a symmetric relation. So if AB belonging to R, AB is in R, that means 2 divides A minus B. So 2 divides A minus B. And if 2 divides A minus B, that means 2 divides B minus A. It is also true. If 2 divides 14, that means 2 divides minus 14. Changing the sign, statement remains true. So 2 divides B minus A. So BA belongs to R. Therefore, BA belongs to R. So for any AB belonging to R, BA belongs to R. Therefore, this relation is a symmetric relation. This relation is a reflexive relation. It is a symmetric relation. Now, third property, transitivity. For transitivity, let AB belonging to R and BC belonging to R. We are beginning from AB belonging to R, BC belonging to R, and we are going to show that AC belonging to R. So we can say that R is transitive. So see, AB belongs to R, that means 2 divides A minus B. This means 2 divides A minus B. And if BC belonging to R, BC belongs to R, then 2 divides B minus C. So 2 divides B minus C. That means if 2 divides A minus B, that means A minus B is an even number. So it is 2 times M. And if 2 divides B minus C, then B minus C is another even number. So it is 2 times N for integers M and N. Now adding these numbers, A minus B plus B minus C, it is equal to 2 times M plus N. That means BB is cancelled. So A minus C is 2 times M plus N. So it is proved that A minus C is an even number. So that means 2 divides A minus C. So AC belongs to R. Therefore, this relation is a transitive relation. So we have proved that. Thus, relation is a reflexive, a symmetric, and a transitive And if any relation satisfies these conditions, then it is said to be an equivalence relation. Therefore, this relation is an equivalence relation in given set Z. So we have proved first part of the question, that prove that this is an equivalence relation. And to come on this topic, we need equivalence relation. Let R be an equivalence relation. Existence of this word, validity of this word is for equivalence relation. If any relation is equivalence, then and only then we will discuss about equivalence classes. So because this is an equivalence relation, now here we will discuss about equivalence classes or partitions of Z, that is the second part. So to understand second part, that means application of this definition. So now coming on this definition. Now see, here R is an equivalence relation in Z. Let R be an equivalence relation in set A. Here Z is in place of A. Now we take any element X belonging to A, that means here we are taking element belonging to Z. So here Z is set of all integers. This is Z. Suppose I take, first of all I take 0. So say 0 belongs to Z. Now equivalence class containing 0 is denoted and defined as, keep 0 in box. Say here equivalence class containing 0. Equivalence class containing 0 is equal to set of all y belonging to, here we have Z, relation is in Z, in definition word is A, y belongs to Z such that xy belonging to R. What is x here? 0. So 0y belonging to R. That means set, it is nothing but set of all numbers from Z which are related with 0. All numbers which are related with 0. That means this is set of all integers from Z such that if 0y belongs to R, that means 2 divides 0 minus y. That means 2 divides 0 minus y. See, exactly I am putting similar to this definition. So that is, now see, set of integers such that 2 divides 0 minus y, that means this is y minus y, 2 divides minus y. Now when 2 divides minus y, if y is even, so from this Z, if we take even numbers, say here even numbers are, if I keep here minus 2, then 2 divides minus of minus 2. If I take here 0, taking y equal to 0, 0 minus 0, it is also divisible by 2. Put here 4, sorry, put here 2. So 2 divides 0 minus 2. So 2 divides this number, that means this is even. minus y is even if y is even. So I am putting here all even numbers, 2, then next is 4, next is 6, like this. That means set of all numbers which are related with 0. These are numbers which are related with 0. Say 0 minus 2, 0, 0, 0 is related with 2, 0 is related with 4, 0 is related with 6. That means these are in R. These all elements are contained in relation R. Because difference a minus b is divisible by 2. So 0 is here fixed. So these are the numbers which are related with 0. So equivalence class containing 0 is nothing but set of all numbers from given set which are related with 0. Now similarly, we take 1. We are taking equivalence class containing 1. So now say 1 belongs to Z. Here Z is Z. 1 belongs to Z. Now I keep here 1. Equivalence class containing 1. It is set of all y belonging to Z such that here we have taken 1. So 1y belonging to R. X is replaced by 1. So this is the set of all numbers which are related with 1. That means it is set of all numbers such that 1y belong to R, 1y belongs to R, that means 2 divides 1 minus y. So 2 divides 1 minus y. Now 2 can divide only even numbers. So value of this must be even. Now 1 is odd. 1 is odd, and from odd number if you subtract odd, then odd minus odd it will be even. So now we are taking those numbers y such that this must be even, because 2 divides only even numbers. So let me take all those y from Z. Now see, 1 minus y is even if y is odd. So taking odd numbers. So odd numbers are minus 3. If you keep here minus 3, then 1 minus minus 3 is 4. So 2 divides 4. Then after minus 3, take minus 1. If you put here minus 1, then 1 minus minus 1 is 2. 2 divides 2. Then take 1. If you take 1, so 2 divides 1 minus 1. Put here 3. 2 divides 1 minus 3. Then put 5. So this is the set of elements which are related with 1. See, 1 minus 3 belongs to R. 1 minus 1 belongs to R. 1 3 1 1 belongs to R. 1 3 belongs to R. 1 5 belongs to R. See, this one is common. These numbers are related with 1. So set of numbers related with 1, it is here. So this is said to be equivalence class containing 1. You can see that, see, 1 is here. This is equivalence class containing 1. Say here 0, 0 is here. Whatever you keep here number, same number will be in that set. So this is equivalence class containing 0. This is equivalence class containing 1. So discussion for 1 is done. Now for 2. Equivalence class containing 2. class containing 2, so I keep here 2. So that is y belonging to z, a is z, 1 x we have taken 2, so 2y belonging to r. Equivalence class containing 2, it is set of all y which are related with 2. This is 2. That means set of all y if related to 2, that means it is set of all y such that 2 divides 2 minus y. Now 2 can divide only even numbers, so this should be even, and to make it even, because 2 is even, we have to subtract only even. If you subtract odd, then this difference will be odd. So to have this difference even, you have to subtract even from 2. So y we have to take even values. So here this is set of, see here if you take 7, then what is 2 minus 7? Minus 5. But 2 does not divide minus 5. So we can't take y7. It happens because if you take y odd, so don't take odd to make this even. If you take here 8, so 2 minus 8, that is minus 6. It is divisible by 2. So y equal to 8 is allowed. Then if you take 9, then not allowed. If you take 10, it is allowed. If you take 11, not allowed. If you take 12, it is allowed. So to make this even, we have to take y we can take even number. So here we keep all even, that is minus 2, 0, 2, 4, 6 and so on. This is equivalence class containing 2. So you can see that 2 is here, equivalence class containing 2. Then, so discussion for 2 is done. Now turn of 3. Equivalence class containing 3. Equivalence class containing 3. Now replace x by 3. So it is set of all y belonging to z. Here E is z. In definition it was symbol A, here symbol is z. In example, y belongs to z, xy, x is 3, 3y belonging to R. That is, it is set of all y which are related with 3 or related to 3. So here this is true if 2 divides 3 minus y, and 2 divides only even. So to make this even, we have to select value of y odd, because 3 is odd. So from 3 you have to subtract odd number, then you will get that difference even. So here I am taking odd values, so that is minus 3, minus 1, 1, 3, 5, etc. So this is equivalence class containing 3. Similarly, we can put for 4. We can continue by this way. Similarly, equivalence class containing 4, that is put here 4. Already 4 will be there. So set of elements which are related with 4. Set of elements which are related with 4, that means 4 minus y is even, and 4 minus y is even if y is even. So we keep here all even numbers, minus 2, 0, 2, 4, 6, etc. So this can be continued. So say these are equivalence classes. Now observe here. Say equivalence class containing 0, equivalence class containing 2, say these are same. Equivalence class containing 4, these are same. So it is clear that here it is clear that equivalence class containing 0, equivalence class containing 2, equivalence class containing 4. If you find equivalence class containing -2, here these are same, and equivalence class containing 1, equivalence class containing 3, equivalence class containing 5, that means equivalence class containing 1, equivalence class containing 3, 5, or if you find for -1, these are same. And say if you take union of these two sets, say this set contains all even and this set contains all odd, all even, all odd, and if you join them, union, if you take union of class containing equivalence class containing 0 and equivalence class containing 1, then union is Z. Here equivalence class containing 0 union equivalence class containing 1, it is Z. That means take this set and take this set, their union is Z. And see one more thing, these are disjoint, these sets are disjoint. Intersection is null set, where intersection of this is empty, they are disjoint. We are getting only two sets, set containing even numbers, set containing odd numbers. Same set is repeated. Z is divided in two parts, Z is divided in two sets, both are disjoint, whose union is Z. So these two sets are partitions, partitions of Z or equivalence classes of Z. Equivalence classes for this relation. Now see, we found equivalence class by this definition. Now look here, if x1 x2 belonging to A, then either equivalence class containing x1 and equivalence class containing x2 are equal, or their intersection is empty. Only two possibilities. From these equivalence classes, select any two. Select any two. Class containing 0, equivalence class containing 1, equivalence class containing 2, equivalence class containing 3, equivalence class containing 4. Select any two. You can see that if you selected even numbers, then equivalence classes containing them are equal. If your selected number, one number is even, one number is odd, then their intersection is empty. See, intersection of here, if you take 2 and 3, see, equivalence class containing any even number, equivalence class containing any odd number, intersection is empty. This set contains all even numbers, this set contains all odd numbers, nothing is common, they are disjoint. And if you take all equivalence class containing 2, equivalence class containing 16, so this will be equal. If you find equivalence class containing 3, equivalence class containing 35, these are equal. So if x1 and x2 both are even or both are odd, then these sets are equal, otherwise intersection is empty. So say that is the here statement. x1 x2 belonging to z, two numbers are integers, then either equivalence classes are equal or intersection is empty. That is, any two equivalence classes are either disjoint or equal sets. If you find equivalence class containing any number from given set, and if you observe this property, then either equivalence classes will be same or intersection is empty. And every equivalence class, it is subset of A. Here A is our Z. See, this is subset of Z. 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 See, these sets are subsets of Z. Here relation R divides given set, here Z, into mutually disjoint subsets called partitions or subdivisions of here Z. So this relation divides given set Z in two disjoint sets, set of even numbers and set of odd numbers. Then same sets are repeating. The union is Z and intersection is empty. So these two sets are said to be partitions or subdivisions. Relation R divides A into mutually disjoint subsets Xi called partitions or subdivisions of A. Now I replace here word symbol for this example Z. So relations R divides given set Z into mutually disjoint subsets, equivalence class containing 0 and equivalence class containing 1, called partitions or subdivisions of A. So see here, equivalence class containing 0, that is -2, 0, 2, 4, 6, and class containing 1, that is these are partitions of Z. Z or equivalence classes. So here we are getting two partitions. Sometimes we get three partitions. So when we get three partitions, so first partition, second partition, third partition, then again it will be repeated. First partition, second partition, third partition, first partition, second partition, third partition. Sometimes you will get here 5 partitions. So if you are getting 5 partitions, then you will get first partition, second partition, third partition, fourth partition, fifth partition. Then this will be repeated again. Same, repeated again. The first set will be repeated. First, second, third, 4, 5, like that. Here first partition, second partition, again first partition, second partition, again first partition, second partition. Only 2 sets are repeating. So these are partitions or equivalence classes. So that is meaning of this statement. And these partitions are satisfying these conditions. All elements of Xi are related to each other for all I. See, if you select any two number from any partition, both are related to each other. 2, 4 belongs to R. 4, 6 belongs to R. If you take two numbers from another partition, 5, 7 belongs to R. 3, 5 belongs to R. 1, 3 belongs to R. If you select both numbers from same partition, then that ordered pair including those both selected numbers belong to R. So they are related to each other. 2 is related to 4 or 4 is related to 2. 2 is related to 6 or 6 is related to 2. 5 is related to 7 or 7 is related to 5. But if you select a number from this partition and another number from other partition, different partition, suppose 4, 7. So 4 is not related with 7 because 4, 7 does not belong to R, because 2 does not divide 4 minus 7. So when two elements are selected from different partitions, they are not related to each other. No elements of xi are related to any element of xj. That is meaning of that explanation. No element of xi, say here consider 0, no element of equivalence class containing 0 are related to any element equivalence class containing 1. So if different partitions, from different partitions, if you select elements, then they are not related to each other. And union of all partitions is given set. Here it is Z. Union of, here there are two partitions, so union of both partitions is Z, and their intersection is empty. Union of all partitions is A and their intersection is null set. This means these are different, these numbers are different, partitions are different. So that is meaning of partition and equivalence classes. So that relation are in the set A given by this set R, relation is set of all AB such that modulus A minus B is E1. This is an equivalence relation. So first of all, let me finish this part. We show that this is an equivalence relation. Say here R is equal to AB such that mod A minus B is E1. This is a relation in set A. Here A is 1, 2, 3, 4, 5. First property, reflexive. Say for every A belonging to A, if we take any A belonging to A, then modulus A minus A is E1. This is 0. Modulus A minus A is E1, so AA belongs to R. Therefore, R is a reflexive relation. R is a reflexive relation. Second property. Second property, let EB belonging to R. We are going to check symmetricity. Is R symmetric? So beginning from AB belong to R, we are going to show that BA belonging to R. For every AB belong to R, if BA belongs to R, then we can say R is a symmetric relation. So now say, let me join this link. AB belongs to R. If AB belongs to R, so modulus A minus B is E1. If modulus A minus B is even, then obviously modulus B minus A is also even. So it is done. Mod B minus A is even, so BA belongs to R. So this is symmetric. Third property, going to show check transitivity. For transitivity, let me take AB belonging to R and BC belonging to R, taking a pair of elements in which B is in common. See, B is in common. Now we want to check that AC belongs to R. We want to reach at this step, AC belonging to R. If we can show AC belongs to R, then it is symmetric. Sorry, transitive. Now see, AB belongs to R, that means A minus B is even. Modulus A minus B is even and modulus B minus C is even by this definition. Modulus A minus B even because AB belongs to R. BC belongs to R, so B minus C is even. Now A minus B is modulus of A minus B is even, so A minus B is 2m. A minus B will be even. Add B minus C. A minus B is even, B minus C is even. That means A minus B is 2m and B minus C is 2n. So sum of these numbers, A minus B plus B minus C, is 2 times m plus n. Therefore A minus C is 2 times m plus n. So A minus C is even. A minus C is even, so modulus of A minus C is even. So what is proved? It is proved that AC belonging to R. So AB belonging to R, BC belonging to R, from which we have proved that AC belonging to R. Therefore, this relation is a transitive relation. Thus, given relation R is a reflexive, it is a symmetric and a transitive. Therefore, R is an equivalence relation. So first part is done, it is an equivalence relation. Now next part of the question. We want to show that all the elements of this set are related to each other. So say that we show on this side all the elements of 1, 3, 5 for all AB belonging to 1, 3, 5. If we take any two numbers AB belonging to 1, 3, 5, that means both are odd numbers. A is odd, B is odd, and difference of odd and odd, it is even. Difference of two odd numbers is even. So their modulus value is also even. That means AB belonging to R. So A is related to B. Therefore A is related to B, or we can say B is related to A. So what is proved? It is proved that all the elements of 1, 3, 5 are related to each other. Therefore all the elements of 1, 3, 5 are related to each other. Now, next, show that all the elements of 2, 4 are related to each other. Now, discussion for 2, 4. For all EB belonging to 2, 4, if both numbers are taken from this set, then both are even. If both are even, that means E1 minus E1 is again E1. So their modulus is also E1. Therefore, again, AB belonging to R. That means A is related to B. So A is related to B. So all the elements of, therefore, all the elements of 2, 4 are related to each other. Now, again, go ahead, but no element of 1, 3, 5 is related to any element of 2, 4. So let me take A from this set and B from this set. So let E belonging to 1, 3, 5, A from this set and B from this set, and B is from 2, 4. A is odd, B is even. And if you take difference of odd and even, odd minus even is odd. So difference of odd and even is odd, means it is not even. This value is not even, and if a difference is not even, then AB does not belong to R. So AB does not belong to R. So A is not related to B. Therefore, A is not related to B. That means if we take any element from this set and other element from this set, then they are not related to each other. So that means no element of 1, 3, 5 is related to any element of 2, 4. So AB belongs to R, that means A is related to B, or B is related to A. Now question is, let L be the set of all lines in XY plane. L be the set of all the lines in XY plane and R be the relation in L, defined as, say here, R is defined as, it is set of ordered pairs L1, L2 such that L1 is parallel to L2. This is a relation in L. It is a relation in L. What is L? L is set of all lines in XY plane, where L is set of all lines in XY plane. Now we want to show that R is an equivalence relation. So first property, reflexivity. We take any element from L for any line L belonging to L. L is set of all lines in xy plane. So if we take any line L from this set L in which relation is defined, then L is parallel to L. It is true. And if L is parallel to L, that means LL belongs to R. So R is a reflexive relation. Second property, for any ordered pair AB belonging to R, we want to check its inverse BA. Does it belong to R? That now we are checking. Let LM belonging to R. Any element LM belonging to R. Now LM belonging to R, that means L is parallel to M. So L is parallel to M. If L is parallel to M, that means M is parallel to L. That is true. M is parallel to L. So ML belongs to R. That means ML belonging to R. So therefore, R is a symmetric relation. Third property, transitivity. Let LM belonging to R and MN belonging to R. Say here, these are lines, elements of this set, lines in xy plane. So these are lines in xy plane. LM belongs to R, that means L is parallel to M, given. LM belong to R, so L is parallel to M and M is parallel to N. If L is parallel to M, M is parallel to N, that means L is parallel to N. So Ln belongs to R. So what is proved? R is a transitive relation. R is a transitive relation, thus R is a reflexive, a transitive, a symmetric and a transitive. Therefore, it is R is an equivalence relation. R is an equivalence relation. So this is proved. Now we want set of all lines, set of all lines related to line y equal to 2x plus 4. Set of all lines related to y equal to 2x plus 4. That means, it means equivalence class containing, equivalence class containing this line, containing line, let me say it is L, it is y equal to 2x plus 4. Set of lines, set of elements related to, set of elements related to any element x. That means equivalence class containing that element x. That means It is set of all L, set of all L belonging to, say we have to differ the symbol, I should take different symbol, M, set of all lines M belonging to L, belonging to L. What is L? Lines in xy plane. That means it is set of all lines belonging to xy plane such that M is parallel to L, such that M is parallel to this line containing line L. Let me keep only equation y equal to 2x plus 4. That means M is a parallel to line y equal to 2x plus 4. Equivalence class containing x. That means set of all y belonging to A such that yx belongs to R. So here we can put one more notation in detail such that ML, such that M here, this is y equal to 2x plus 4 belonging to R. Set of all y such that yx belongs to R. This means M is parallel to y equal to 2x plus 4. That is, it is set of all M such that M is parallel to y equal to 2x plus 4. If L1, L2 belongs to R, means L1 is parallel to L2. L1, L2 belongs to R, means L1 is parallel to L2. That is, it is now, if any line is parallel to y equal to 2x plus 4, then that line can be expressed as y equal to 2x plus c. All the lines which are parallel to 2x plus 4, all the lines which are parallel to 2x plus 4 can be expressed as y equal to 2x plus c. C is any real. So this is equivalence class containing y equal to 2x plus 4.